Very warm welcome to the first edition of the Indian Electronics and Semiconductor Association Future Skills Campus Connect Inspirational Series, monthly series. The Indian Electronics Semiconductor Association is looking to reach out to students, high schools as well as undergraduate. We're looking forward to participation from the faculty, both UG and PG. We'll be having a small feedback form for you to fill, please. And it gives me great pleasure to introduce our speaker, Dr. Pradeep Thakur. Dr. Pradeep Thakur has over 30 years of experience in the semiconductor industry and is currently the India country head and vice president of engineering at D-Matrix, an artificial intelligence startup company. And with that, it gives me great pleasure. He's a leader for the Indian Electronics Semiconductor Association Campus Connect program. It gives me great pleasure to hand over.
Thank you, Sharath. Appreciate the introduction. Thank you so much. Hello, everyone. Welcome to this first edition of the monthly series that we are bringing to the students, parents, and faculty to demystify the ESDM buzz that's taking place in India as well as globally. In this first series, I'm going to be covering the overview of what ESDM segment is really about. And I'm going to be focusing on the four pillars, one being the technology overview itself, second one being the opportunities and the challenges that this segment has currently as well as over the coming decades. And I'm going to talk about the career prospects as well as the educational routes to land a promising career in the emerging renewed thrust on the ESDM segment in India as well as globally. Thank you so much. With that, we must first celebrate the success of our nation as a Chandrayaan-3 and congratulate ISRO and the entire team for the grand success in the space electronics space. And with that, I would like to jump into the main agenda of the topic today. I'm going to be covering the introduction of the ESDM sector. Within the ESDM sector, I'm going to talk about chip manufacturing, followed by chip and system design, and then go into the education routes as well as the career options within this sector. And most importantly, I want to talk about why now. This sector has been around for more than 4 decades, and now it is picking up even further momentum. And I want to talk a little bit about why it's relevant now for India, as importantly for the talent in India, for the opportunities that are there in India as well as globally. So with that, let me first and foremost talk about what is ESDM. So ESDM stands for E for electronics, S for system, D for design, and M for manufacturing. So ESDM basically covers the entire gamut of electronic system design and manufacturing. In that, what is electronics and system? So electronics and systems are pretty much all around us at home, office, schools, colleges, even vehicles, hospitals, leisure, toys, space, defense, and so on. Electronics and system has presence that is ubiquitous. Today, our day-to-day life actually heavily relies on the functioning of the electronics and the systems. When you think about a system, it is basically anything and everything that is associated with electronics, and it brings you a human experience, whether it is in form of communication, whether it is in form of transportation, whether it is in form of education. There are many aspects of electronic systems that are now permeated in our day-to-day human experience. And it is hard for many to believe that some of these things that we're experiencing today didn't exist 20, 30 years ago, or even 10 years ago. But today we are completely reliant as a need that exists for our day-to-day life. System is made up of two components, hardware and software. And hardware is primarily composed of electronics, So if you think of a system, a laptop, or a computer tablet, that's one example of a system that you actually experience, variety of applications from video gaming all the way to, documentation, projects, programming, etc. And then what makes this hardware work is a critical component of the software. So hardware and software working together composes a system, and that system brings us an improvement in the standard of living. What is electronics made up of? So electronics is made up of what we refer to as a printed circuit boards, chips, resistors, capacitors, wires, inductors, and so on. So these are all various components that make the electronics. So what you see on the left side in the green is referred to as a printed circuit boards, which has many discrete components uh, on the board. And these components are what we just discussed, from chips to resistors and so on. What are chips? So chips is a somewhat of a generic term that is used to describe integrated circuits. And integrated circuits are also referred as micro circuits, nanoelectronics, VLSI circuits, silicon technology, semiconductor technology, and so on. So there are many terms, but all of that basically goes on to defining what chips are all about. Let me cover a little bit a stepping back on how we arrived where we are at today with the technology. So when you think of human civilization and entire history, I guess it all started with use of fire, and then leading up to human settlements and transportation and whatnot, right? Leading to making cities and towns and so on. And agriculture, I guess, was a main turning point. Uh, However, at certain point in time in the human history, there came a major shift in our attitude to understand the world around us, and we took on the spirit of scientific inquiry. And once the spirit of scientific inquiry came, the journey of technology and the usefulness as well as the intervention and invention started. And this has been on for many centuries. uh, the particular points of inflection that came out of scientific inquiry was industrialization, automation in mobility, transportation, invention of cameras, and so on. And in particular, in last 125 years, what we have seen is a discovery of electricity, invention of computers and communication technologies. Cell phones are ubiquitous today, but they didn't exist just a few decades ago, right? Space technology, we all saw Chandrayaan 3, and we just heard of the Aditya L1 launch as well. Uh, then came the invention of the semiconductor technology, and that accelerated the power of embedded software. And semiconductor technology, along with electronics and embedded software, is what we just talked about as systems. Then came the internet, and now we are just at the cusp of AI/ML, and it is already so impactful. So last 125 years have been really very transformational for the way we have lived lives as humans on this planet. And with the advent of AI/ML, it's hard to imagine what next 100 years would be like. But one thing for sure, that the technology continues to grow its pace in a human life, and it continues to create opportunities for innovation. It continues to create opportunities to improve human life and experience, and thus also create opportunities for employment, opportunities for innovation, opportunities for uh, good businesses, and all in all, it basically leads to taking a good life to a great life, and balancing it well. If you really think about this common phrase that mother is necessity is the mother of all inventions, well, that is not necessarily true. What inventions that we have seen that happen in last century are primarily an outcome of two factors. One is the mass education systems that came about, uh, with an emphasis on the scientific temperament and the spirit of inquiry. And that is what led to many discoveries as well as inventions. And second important part is uh, visionaries that innovated, and they drove changes into the human behaviors as well as the asks from us on what we need to have a good experience of life on a day-to-day basis. Today we go to hospitals for anything from minor surgeries to ECGs or whatnot. All of that runs on technology. Much of it runs on electronics with interdisciplinary uh, productization of solutions that are of use to us. So as we grow further, as we grow further in the ESTM space, and we speak of visionaries that have really changed the way we experience life in last 100 years, there is really no moving forward without remembering Dr. Jack Kilby and Dr. Robert Noyce. Both of them, on a parallel path, invented uh, integrated circuit, or what we call as a chip. Uh, and what I'm showing you on the left side at the bottom here is the first integrated circuit that Dr. Jack Kilby created in 1958. And this is a single transistor, simple circuit which changed the world, if I may say. Today, that simple circuit looks to be something like what you see on the right hand side. This is a single transistor. Here, what you're seeing is trillions of transistors. This circuit, what I've shown here, is about 1000x bigger than what it would be in reality. In reality, this entire circuit on a chip would be just like this one square. It will all fit into this one square. This is an enlarged image, and in this picture, what you see has wires that would a city of Delhi or Mumbai or Bangalore would have, an entire city fitting into just a small, few millimeter by few millimeter area. And that level of compaction of putting circuits, wires into a very small area is why it is being referred to as a microcircuits or nanoelectronics and such. Now, revolution that started with the invention of the first IC and what it has led to today is also a very lucrative large industry which is worth almost $3 trillion worldwide, and about $500 billion worth of that is just the chip or the IC sector. In India, we are at about $118 billion of the electronics industry, and we are expected to grow almost threefolds in next 5 years or less. And chip and the IC components that we do the imports today is roughly about $22 billion, and it is expected to grow to about $66 billion. And all of this is being imported as of today, which has a potential of being locally made and manufactured. So why is ESDM industry crucial for India's vision today? If India wants to grow to a $1 trillion economy, we have done really well with our agricultural, with our export sector, with our software exports. That there are many export and other local industries. Now, looking at the size of the ESDM industry and where we are at as a nation, there is a huge potential to add value to our economy to grow towards $1 trillion or more. And what are the aspects that are available to us as opportunity for the country? So in our country, the chip industry started about 35 years ago, and we got well established as a talent destination. Many homegrown companies as well as many multinational companies have found talent in India to support their missions. And we also have been the sourcer for the worldwide skill needs in the chip design all over the world. That success has given our talent a credibility, our nation a credibility, and there is a significant growth ahead in that particular field that we are going to see bring more opportunities in India as well as create more opportunities for the talent in India for a global journey. In addition to that, India itself, as well as other countries like US and such, are now foraying into or relooking into chip manufacturing. And chip manufacturing is a high volume uh, fabrication of the semiconductors and components that is also going to create many new opportunities as well as add fuel to our economy. In addition to that, we have been a hub of system design and manufacturing, particularly with cell phone industry for quite some time. And now we are seeing newer industries coming into the country with our own indigenous system design and manufacturing also taking shoots and roots and growing from there. So all in all, if I may to say, the ESDM segment now is really ripe with many well-paying jobs locally as well as globally. And it is bringing great opportunities to the entrepreneurs who would like to have their own journey in the ESDM sector. Having said that, let me talk a little bit about what are the chips, ICs, or semiconductors, and why this is going to be something very basic. Those among us here who come from the semiconductor background, these are very basics. For those among us here joining from high schools or otherwise, I just wanted to take a little bit of time and explain what the electronics is made up of. So electronics is entirely based on binary number system. The binary number system is a base 2 numerical system in which every number from 0 all the way to infinity minus 1 can be represented with a sequence of zeros and ones. So these are the only two symbols that are used. And 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4. So with the combination of these digits or these bits, not digits, but the bits, you could represent any number in the numbering system. You can also do the math in binary number system with addition, subtraction, multiplication, division, and so on, and very complex matrix multiplications and such. In addition to that, the main languages of our communication worldwide with many kinds of keyboards existing. Here I'm just showing an example of an American standard code, which is what our English keyboards are made up of. But today keyboards exist in many languages of the world, and pretty much every alphabet is mapped to a unique code. And that basically transforms any interaction between a human and electronics into a binary number system. Once you have a binary number system, you're dealing with 0 and 1, and how they are being sequenced, which is what forms the basis for digital electronics. Digital electronics, just like a home, you have a switch. And when you turn the switch on, the current flows, and that is being referred in digital electronics as logic 1. When you turn the switch off, the current stops, and that's being referred to as a logic 0. So this is logic 1 and logic 0, which forms the base for the digital electronics. And that's what eventually leads us to build very complex electronic systems. The current or the flow of the current is basically the flow of electrons, and that divide everything that we see around us mostly into conductor and insulator. So metal like copper is a conductor, which is used in house wiring. You turn the switch on and instantaneously you see the fan turning on or the light turning on because the current flows through conductor relatively easily. Then the second category is insulator, which is such as glass or dry wood, where if the wires were made of glass or dry wood, the current would not flow through it. And even if you turn the switch on, nothing will turn on the other end because there is no current that can flow. So these are the two categories based on based on the material that supports the flow of current or not. Now there is a third category which we refer to as a semiconductor. Semiconductor is an insulator material as a base, but it has a unique property that when that material is heated or when it is subjected to a specific voltage, it becomes a conductor. So semiconductor basically now allows one to make small micro switches that you can turn on and off based on the voltage that you apply. Certain voltage you apply, it becomes a conductor. You turn off that voltage, it becomes a insulator. Similarly, temperature also affects the flow of the current through the semiconductor. So semiconductor basically forms a base of electronics engineering. Here what I'm showing you is a PMOS representation, which is when you apply the logic value, this is being referred to as a gate, then you have a source, and then you have a drain. When you apply the logic value, when you apply a voltage to the gate, the current flows from source to drain. When you turn off the voltage at the gate, the current stops from source to gate. And so this is basically a switch that turns on and off. Similar to PMOS, there is another technology called NMOS, which has the same function, but the voltage property to turn on and off the gate or the switch is different. When you combine both of them together in this formation, it is being referred to as a CMOS or a complementary MOS technology, where you have a PMOS and when you have an NMOS working together. This basically forms what we refer to in a colloquial term as an inverter. When you have an inverter, whatever value that you apply at point A, you get the reverse value at the point B. If you apply logic 1, you get logic 0. You apply logic 0, you get logic 1. And this inverter in our symbolic representation is shown with a triangle and a bubble that you see here. The next concept is how do you make an inverter in the CMOS technology? Now, I'm going to talk about the fabrication process at a little bit of a highlight level later. But here, what it goes to show how the PMOS and NMOS are made. And when you make the PMOS and NMOS, what you see here is a gate, which is what I was referring to as a gate here. And gate of PMOS and NMOS both are connected together. And what you see then is a source and drain, and of course the bias. And with source and drain, now you basically have a circuit that is ready to make what we refer to as mask, which is a start of the fabrication process. This is a concept representation. The layout or the physical implementation representation of an inverter looks something like this. And in this session, we will not be going, but in subsequent monthly series, there will be an opportunity of exactly what this layout actually means and how it's being defined, how it's being derived. Today, I'm just going to show a picture and just show you the representations from circuit to symbolic to concept to physical implementation. And from there, I'm going to talk a little bit about what happens after the layout is done. And when the layout is done, the process that begins, that process is referred to as a fabrication process. And that fabrication process is also used for mass production or the manufacturing of the chip. So when you look at the ESDM sector, in the ESDM, it's E for electronics, S for system, M is for manufacturing. And here, over next 3 slides, I'm going to talk a little bit about the manufacturing. The manufacturing or the fabrication of the chip actually starts with sand. One of the major constituents of the sand is silica, which is a silicon dioxide, SiO2. And the silicon dioxide is then, so basically the sand or the silica is then processed through many steps of thermal, chemical, and physical processes so that you can extract high-grade silicon crystals. And then once you have high-grade silicon crystals, what we make with it is what is referred to as a silicon ingot, which is basically a cylinder of the silicon. Once you have the cylinder of the silicon, it is sliced in a certain thickness that is specified here. And those are referred to as wafers. And once the wafers are done, we go through multiple steps to populate the wafers with the circuit. And those wafers are referred here as pattern wafers, which then are cut vertically and horizontally in a dicing so that we get individual dies. And each die has a circuit. And as I said, each die, and actually some of the dies are literally the size that you see in this picture and contain billions of transistors. And hence they are the microcircuits or the nanoelectronics. Once these dies come out, the next thing that happens is testing of the dies. And the dies that are found to be correctly built go further to be placed inside a package. the dies that are found to be incorrectly built in the manufacturing process, in the fabrication process, are basically thrown away. That good dies that go into the package then go through the part testing, where the package part are again tested, because when you put a die inside a package, there could be something that could go wrong in the process and break the circuit or break the behavior of the packaged die. So the testing is done again, and then the dies that are found to be good are then shipped to the customer. Fabrication process takes place into what we refer to as a clean room, in order to make sure that the circuits are correctly constructed. It is important to have no pollution of any kind in the room, whether it is smoke particles, whether it is dust particles, whether it is vapor particles. So the fabrication process of the dies is done in a very controlled environment, where humans put on the PPE kind of a suit. The environment of the room is maintained to the specifications, and this is basically being done to make sure that the chips that are being fabricated come out correct to the largest possible percentage of the total wafer. What you see here next in this picture is a march of the technology that basically started growing the wafers. The journey started at about 4-inch wafer, then went to 6-inch, then 8, 12, and now we are going for 18 inches, right? This progression of the wafer size is not just a simple scaling. This is very complex silicon technology, and tons of research went on since 1970s almost, to ensure that we can grow the size of the wafer. Now, why do we need to grow the size of the wafer? Because the chips themselves started growing. In the very early days, the die contain roughly about 2,000 gates, or even some cases there were even 500 gates. And then it started growing to hundreds of thousands, and then to millions, and so on. So the die sizes started getting bigger, and when you have more die sizes, as you see in this function, as the die sizes increase, the number of dies that you get from a single wafer reduces, and to keep up with it, the size of the wafer also grows. And as the dies grow, the functionality, the amount of functionality you can pack in a single die also grows significantly. So it's all, it's an interplay of technology and economics. The second aspect that is crucial here to remember is what is being referred to as a Moore's law, which is an observation that the number of transistors on a single chip has been on a trend to grow to be about double every couple of years. And the process that is happening behind is, for example, that you see here, when in the very early days, in 70s and 80s, we used to have 3000 nanometer as an underlying technology to make the dies, to make the chips. And again, through significant innovation and research into process technology, it has been reducing all the way now to we are at about 3 nanometer process node today, and 2 nanometer and below is where the size of the atom comes in. So we are in a very advanced process node, and from here onwards, there is an expectation. Again, there is tons of research going on. There are some really great research opportunities available for the PG and PhD scholars and so on what next. How do we go beyond 3 nanometer, or rather below 3 nanometer? And how do we continue pushing our journey to make semiconductor manufacturing an attractive economic option? So the way the process node continued reducing from 3000 nanometer down to 3 nanometer, up to a certain point, it was being referred to as a scaling trend. And it is basically an area it is basically a reduction in the area of the die, along with the reduction in the power, and increase in the speed with certain tweaks that we make to the fabrication process. And the scaling factor of 0.7 was found to be optimal, where if you were to draw a rectangle and dimensions x and y, if you reduce x and y by 30%, the area reduces by half. So 30% reduction in the dimensions was used as a scaling factor. And that allowed us to put either to reduce the size of the chip if it had the same number of transistors, or we could keep the size of the chip same and put twice as many transistors on the device. So it opened up more possibilities once we started going down the journey of the scaling factor. As you go down the scaling factor, in order to keep the electric field constant, the voltage that you apply in a process also reduces, and therefore the power also reduces. So you have reduction in the area, reduction in the power, and increase in the performance. And today, how do you go further? How are you going to scale beyond where we are at? Is, as I mentioned, is a major topic of research with tons of funding from the governments as well as private entities. Let me talk about what happens after you make a die. Right, once you make a die, the die gets placed. The tested dies, the dies that are good dies constructed well, they get placed inside a protective casing, and that protective casing is referred to as package. So it's a material that surrounds the circuit, and it prevents the die from the effect of the environment or the physical damage during transportation or the usage. And it also provides the connectivity for the die to be placed on the printed circuit board. So packaging technology also has an additional key function where when you're dealing with a very high performance silicon, it also helps in the aspects of thermal dissipation or the power dissipation. So just like the way I showed you the journey of the wafer over the past 4 decades, the journey of the silicon technology itself for past 4 decades, the packaging technology also has been a huge area of research. And that journey almost start is in a lockstep. If you build a new silicon technology, but if you don't have the right kind of package, you'll not be able to build a product. So packaging has also been a very innovative field, where it started with what we used to refer as a DIP, dual inline package. You'll still find some of these components on your breadboard in the college projects, right? And then came, the quad flat packs, ball grid array, pin grid array, ball grid array, and so on. And now we are talking about system in package, where you have multiple dies, you have package on package. And the latest trend that is happening is a 2.5 dimension or 3 dimension integrated circuits, right? So the 2.5D circuit is the one that has side by side placement of the dies inside the same package. And the 3D is where you have a vertical stacking of the dies. So for example, you have a CPU, and then on top of it, you can put a DRAM, and you can kind of build a vertical a tower kind of a structure inside a single package. This is also being referred to as a heterogeneous integration. The heterogeneous integration allows you to put dies fabricated by different suppliers in different technologies, meaning in different process nodes. Could be even optical solutions, not just the silicon solutions. So even there could be different materials. So you could take anything that would have a play within electronics, any kind of a die that has a play in electronics fabricated by anybody, but be able to integrate them. And that is the latest and greatest. That is what is happening. Just the way in the wafer space, 18-inch wafer is the latest and greatest happening. The stack die or the heterogeneous integration is the latest happening things in the packaging technology. Once you have the die, once you have the package, the next discipline that is relevant in the fabrication or the manufacturing of the chip is what is being referred to as a testing, qualification, and characterization, right? So why do we really do testing? So testing, as I showed earlier, it is done at the die level. When you cut the die from the wafer, each die is individually tested to be constructed correctly or not. And then once they're put in the package, they're tested again. So now the chips are tested to be correctly constructed or not. Now, the reason this is done is because the process of making a wafer, as well as die and the packages, integration with the packages, they're all prone to some kind of a defect that can get into the circuit. So even if you have designed it correctly, there could be a manufacturing defect that could prevent the circuit or the chip from functioning correctly in the system. And it is important that such broken devices are not shipped to the customer. And the approach that the industry takes is to every chip that gets manufactured gets thoroughly tested. And what is not tested is assumed to be broken. And that is important because when you ship a part to the customer, you don't want customer to detect that they have received broken parts from you, right? I mean, there's just a simple practice of keeping credibility besides the financial and legal consequences. So when you make a chip and when you don't test, or if you don't test, then what would happen is a bad die will get inside the package. Now, if you find out at the package level that there is a bad die, you have to throw away that package. Now the cost has increased because of the package being included along with the die. If you don't test at the package level, then you test at the PCB level. Well, at that point, you don't have a choice but to throw away the whole PCB, and the cost increases. If you didn't test at the PCB level and it goes into the system, now debugging at the system level is very complicated. And it takes lots of time and skills to do the debugging. So basically, the simple concept is at every stage of fabrication, integration, and deployment, there will be full testing of the chip, starting from die to package die to the piece to the system to the board level, and then to the system level. And if any case, if it is missed, the cost of miss is almost considered roughly about 10x. So testing is a very important part of making industry economically viable. And if you really think about the field of defense or medical or automotive, a malfunctioning chip can cause accidents, it can cause crashes, it can cause wrong diagnosis. So the cost of escape is immense in certain crucial fields as well. So the whole discipline of testing chips is its own career option, and it is very crucial to ensure that the business is successful. What you see here below is what is referred to as a socket. What you see here below is referred to as a load board, and this is referred to as an automatic test equipment. The load board goes inside the automatic test equipment, the socket goes on the load board, and the chip, the package part, goes inside the socket. To test the dies before they're in the package, that technique is being referred to as a wafer probing, where there are very fine probes that may connect to the die and do the testing of the die. So this is the aspect of what we refer to as a test. The second aspects are referred to as a qualification and characterization. So no products are shipped without ascertaining that the product will run for a certain number of years reliably. And this whole aspect goes with the reliability testing, where you do high temperatures testing, temperature recycling, etc. And also you vary the voltage and frequencies, and as well as and test the electrical properties of the chip that you have made. And once testing is successful, qualification is successful, and characterization is successful, that is when the mass production starts and mass shipment to the customer start. Before that, what we refer to as engineering samples, and after engineering samples have been tested, qualified, and characterized, they turn into mass production of the chip and solution. Now I'm going to go into the D for the design, which is part of the ESDM. And D for the design for the chip as well as the system has the same concept, where you start with an idea, convert the idea to the specification, implement your idea in a design, verify that what you have designed is what you intended to design. That is called verification. Then do a prototype build. And once the prototype is built, it is validated. And if any issues are found, the cycle iterates. And if it is successful, then the design, whether it is a system or is a chip, it goes into mass production or manufacturing. So what is a chip design flow? So there are multiple types of devices. I'm just going to flash here, and maybe in subsequent sessions, some of my peers will go into more details of each of this segment. Today, I'm going to leave this here as keywords for you to search and self-discover. What just the way we talked about silicon technology and packaging technology, there is a third dimension, which is electronic design automation. And there are several companies that make very crucial contributions as we went over last 4 decades of growth of the chip and continue to break new barriers in the coming decades. The EDA industry that make tools for us to use uh, to design the chips and the systems are as crucial, and the innovations that are taking place in those are also as crucial enablers for this journey for past several decades and will be for the coming decades. So what I'm going to flash here is what we refer to as a standard chip design flow, which basically starts from specifications and ends in silicon. There are several disciplines here that I'm just going to specifically highlight. There is a design, there is verification, there is physical design, and there is a design for test. And on next set of slides, I'm going to touch upon a little bit on each one of this segment. So when you talk about chip design, there are multiple ways of doing a chip design. There are chip design flows for digital electronics, for analog, as well as for high performance, low power, semi, or the full custom circuits. What you see here is a standard flow that goes vertically, where the specifications can be created using any of these or many others programming languages. The design itself, the circuit itself in digital electronics can also be created with programming languages like Verilog, VHDL, and so on. And what you see on the left side is an example of an adder, how it is designed using a programming language called Verilog. That programming language is then converted through a process called logic synthesis to another programming language representation that is referred to as a gate level netlist, which is basically Boolean equation or the gate level representation or a schematic representation of the function. And then through physical design process, that is converted to what we refer to as a layout. And this is what you see on the left hand side is the layout representation of the Verilog RTL. And this then goes into making masks and fabrication process. The next discipline that we refer to is the chip verification. And in chip verification, there are 3 sub-disciplines: simulation, emulation, and formal design verification. And each of these techniques use a combination of hardware and software, either as a server or as an acceleration platform that may be built with FPGA, and they're available under various brand names. And then there is a formal verification techniques. So all of this effort that goes on with RTL design and verification is basically on it uses a programming language or a coding paradigm, but the differentiation between software programming and hardware design is that in software programming, you need to learn really the data structures and software architectures and so on. In hardware design, you need to learn any of these programming languages along with having strong fundamental knowledge of the digital electronics itself, circuit design, microarchitecture, architecture, and as importantly, the domain knowledge, the communication theory or the automotive, and so on. So programming language is one paradigm in chip design, but it really requires a strong foundational knowledge of digital circuit design and at least one of the domains that is relevant for what you are doing a design or the verification. The third sub-discipline within the chip design is what we refer to as a physical design, which is the process of converting the program into the gates and then gates into the transistors and layout. And this field pretty much has several ancillary knowledge that you need to have, a strong skills in the EDA tools, scripting, library characterization, knowledge of the power performance, area optimization, static time analysis, process node, and such. Once you get through all of this, the last field that I'm going to talk about is what is referred to as a design for test. So when you talk about testing the die and testing the packages, it does not happen brute force. It really requires a certain augmentation in the functionality of the circuit to ensure that it can be efficiently tested at the die level, at the wafer level, as well as at the package level. And that discipline of what circuits you need to add in the functionality is referred as a design for test. And there are various aspects such as scan, ATPG, logic-based, memory-based, mixed signal testing, high-speed interface testing. All of that basically comes within design for test discipline. So that was everything about chip design discipline. I'm just going to talk a little bit about a system design now. So system design is essentially building a solution using hardware components and the software, which is what you see in a picture on the right hand side. Any of this would be referred to as a system or a solution, which basically gives you a human experience of use, of some kind of a meaningful use. The system design can be done in multiple ways. The two primary ways is a system design could be an incremental improvement to an existing solution, or it could be a breakthrough new product domain. When you heard of a story of Apple, right? It was a breakthrough development with many of the applications that came up that were pertaining to entertainment and other stuff. Similarly, when you heard about invention of the desktops or laptops, right? These are the examples of either incremental improvement or the breakthrough product. Incremental improvements or the breakthrough products have a relating aspect. The incremental improvements is to serve the existing market and provide better features. Breakthrough products look to create brand new markets, and thus provide something that we as humans feel compelled to make use of, and therefore we demand more, and then it turns into existing market and then improvements. The solutions can be market driven as well as technology driven. There are pros and cons on what one opts when one does a system design, whether you do a market driven solution or whether you do technology driven solution. Generally, when you think of a breakthrough product, you are driving new technology development, but there has to be a customer in mind at the end of the day. No innovation survives without revenues. No innovation becomes a business success unless it has somebody who wants to spend money to buy that solution, right? So the business success is a lifeblood for keeping up innovation, right? So whether it's a technology driven solution or market driven solution, end customer is the key target to see whether the solution will meet end customers' expectations. The system designs are done in many fields, from ranging from defense, space, consumers, all the way to enterprise and automotive. And there are underlying technologies that are essential for one who wants to build the system to know whether it's compute technology, whether it's AI, ML, communication theory, connectivity, storage, networking, robotics, and controls. So these are all underlying technologies that, in an interdisciplinary way, get used to make a product in any of these domains. And some of the product domains also have overlap that can be used from one to other. For example, internet was originally invented for defense purposes, and today it's a solution that is a highly consumer-oriented solution, right? So this is about system design. I want to pick in one particular field in system design, which is automotive. And in automotive, a revolution started almost 2 decades back. That was being referred to as ADAS, Automotive Driver Assistance System, and it was primarily meant for the road safety. ADAS was built using vision system inside the cabin of the car as well as outside of the car in the surround cameras, lidar, which is a laser radar, as well as in-car networking and compute. What you see in this picture is a high-end vehicle with many features that are provided by that are referred to as ADAS features. And purpose of all of these features is to enhance the driver safety, passenger safety, as well as the road safety for the pedestrians and other vehicles. And there are many features that come under ADAS. For example, the first one is a blind spot monitoring, where when you're driving a car, you're looking at the rear view mirror, you're looking at the two side view mirrors. But still, when you are changing a lane, you do have certain areas that are not in the rear views or the side views, and you feel a need to look over the shoulder before changing the lane. That's the blind spot. So with the camera technologies, by putting cameras in the four, 1, 2, 3, 4 sides of the car, now you get a complete view, a cockpit view of what's happening around you, right? And that way you can avoid any accidents that are resulting from the blind spots as you change the lanes, etc. Similarly, there are ignition locks for any kind of drowsy driver detection systems. There are collision avoidance systems, lane departure warning systems. detecting an object on the road that would maybe moving or not moving, or moving at a very slow speed or at a very high speed than yours. And that is to avoid any kind of collision that is resulting from the speed differential, right? And there are several others here, smart, traffic sign recognition and so on. The smart airbag deployment, the airbag deployment came first, and it was somewhat of a brute force. When there is a collision of certain impact, the airbags would be deployed, and these airbags used to be deployed almost at the speed of the bullet, at almost like 100 miles per hour. And there were many cases being registered where the actual impact of the accident was not that significant, but the driver or a passenger got injured on the face severely because of the impact of the airbag being deployed at such a high speed. And that's when the smart airbag deployment discipline came into research. And now what happens is that with the cameras that are inside the cabin, and there are certain other sensors that are inside the cabin that detect the driver profile, passenger profile, the height, the weight, the body positioning. Some drivers sit very close to the steering wheel, some sit very far, some are tall, some are not. So now they do body profiling, and when the impact happens, depending upon the impact, the body moves forward at a certain pace. So even that impact momentum is now registered. And the airbags are now deployed smartly, where the objective is to prevent an injury, not to cause an injury by mistake or by default, right? So there are a lot of fantastic things are coming into our day-to-day life as we drive the car. And I think one of the most talked about innovation is going from ADAS to autonomous vehicle, and eventually to electric vehicle, right? So these are all part of the system design examples that I'm giving here. So ADAS created a car that was self-aware. It had cameras and other sensors inside and outside, where it knew what's happening around it, what's happening inside, whether the driver is drowsy or drunk or so on, right? So it kind of enhanced the road safety. From there, it went to connected car. And the connected car, using a short range communication, the cars started talking to each other. And when they started talking to each other, they started sharing their exact coordinates, location, distance. But as importantly, they also started sharing the profile of the vehicle, how many accidents that car has been in, what is the kind of accidents, right? So now my car knows what I'm surrounded by and what I would need to see as challenges for me to navigate successfully, right? And it will feed that information to me as a driver, and I'll be more aware if a vehicle approaches me that has a significant track record of past history of accidents. I would be more cautious when that vehicle passes by me, right? So connected cars was the next step after ADAS. And then came adding AI and robotics, and that's what led to autonomous vehicles, where the cars are made of chips and software started having their own judgment about navigating on the road. And today, what we are looking ahead is that as the cars evolve further in autonomous vehicle, they're as good as mobile data centers. There is so much computing happening inside the car. And now that computing is not only about computing, because now you're actually having data, and the data is being exchanged, data is being processed. Well, if I'm sitting in an autonomous car, and if my car does not have a security features built in, somebody could hijack my car without my control, right? So that additional security, data privacy, there are many aspects that are coming in as autonomous vehicles are taking forward compute, storage, connectivity, and AI and robotics and so on. And as we see more advances in the AI and robotics, we're going to see more advanced vehicles, more reliable vehicles on the road. And this is one space that is really dear to my heart. If you really look at our Indian road infrastructure, our highways are in really good shape intercity. But when you look within the city, we have a lot of traffic infrastructure that is not quite standardized as our highway infrastructure. And that presents a lot of opportunities for innovation, for India system design houses or any interpreters who want to look for where to focus to create a new system. So, to drive autonomous vehicles in the city, right, there are many newer technologies to be invented, which is largely ignored by the global players. This is a huge space for us. And some of the technology would also apply to the agricultural industry, which is a big thing in our country, right? So this is just one example I wanted to cover about what scope system design has, or what are the, at least one of the product areas of the system design applications. From here, I want to jump a little bit into education and career options. So to get into the ESDM industry, a student would need at a high school level to take physics, math, chemistry as majors in the STEM subjects. In college, one can opt for diploma, bachelor's degree, MTech, or PhD into the fields of electronics and communication engineering, computer science, triple E, or electronics and instrumentation. Bachelor's degree is a sweet spot to get a foot in the door. MTech allows you to study the specific technology like communication or AI or such. Now, the opportunities that are available locally and globally are in the area of well-paying jobs, good opportunities for the research, as well as some great opportunities coming up for entrepreneurship to start your own indigenous IP creation or new system design and new product design, for example, right? The compensation structure and the pay packages vary depending upon the employer, the location, the economy, and one's own proficiency. The better the one is at the one's own skills, the better the pay package. Of course, the starting compensations usually start in a certain range. Say, if I want to give an example, somewhere around 3 to 7 lakh rupees, kind of a per annum payment for the fresh graduate. But then within a decade, it really sees an exponential growth for a good engineer, and the pay packages beyond decade and a half of a career could run into in India could run into over a crore or crores of rupees, depending upon how good one is at with one's own skills. And of course, there are global opportunities that also are very lucrative for this particular skill domain. This discipline also offers a continuous learning opportunity because it's an ever-changing field. There is a continuous innovation happening year on year. So there is a lifelong career and a continuous learning for those who really like the aspects of learning newer stuff. So if you're a student, either in high school or in undergraduate or PG program, and if you're looking for what could be my opportunity for first job in ESDM, so the one basic requirement in ESDM segment is that one has to have strong fundamentals in electronics, which is our first, second, third year curriculum, and one has to be really, really strong at that. In addition to that, if one likes the underlying technology like a communication theory or automotive or others, and have some understanding of the product domain, plus the CAD and EDA, then one can opt for system engineering job opportunity to start, or can get into chip design as well as into chip verification. If an individual has strong fundamentals in electronics and also has picked up the CAD EDA related applied skills, then design for test, physical design are also lucrative options as a first job to get into the industry. And with the chip and system manufacturing taking off in India, this will also create a lot of new opportunities. And the number that I hear could be as much as 12 lakh new jobs that will be coming up in the coming years in the country, and almost close to over 2 lakh plus jobs coming up in the front end itself, right? So there is a huge vacuum of rightly skilled engineers to step into this field. And I cannot emphasize enough, but having really good fundamentals of electronics and picking up hands-on skills are the most important requirements. And then you can add on and then navigate your career through design, DV, and so on. But the most important thing here is that now this field is so large and so wide that there is a lot of specialization that is required in each vertical of the skills, and that is where it really takes the whole team to build a chip. So one can get into design and then maybe grow into verification, or can choose to stay in design. There is just plenty ahead for a career lasting experience and success in this field. The other question would be, who are the top employers in the ESDM segments, right, in India as well as in the globally? So the employment opportunities are there in the field of EDA, in the fabrication, in the ATMP, chip design, system design, and so on. you just Google yourself, and I just Googled it because I didn't know how to pick the top employers myself. I could look at market cap, I could look at revenues. I just said, let me just search who are the top 10 or top 15, and then the list popped up on Google, right? So these are some of the very well branded names in ecosystem. In addition to that, we as a India Electronics and Semiconductor Association, we have 300 plus member companies, ranging from startups to multinational companies to Indian companies and so on. And you can go to our website and you will see them scroll, and these are all fantastic, entities that are doing some exciting work. And exciting entities always need passionate individuals who want to join the journey, right? So you can go to our website and you will find many more names there as well. We also have a tab, academia. You could click on that and you'll get a lot of resources for many questions that you may have. uh, so why now? Why are we talking about this now? I already touched upon this a little bit. We have been having a close to 4 decades of very successful track record as a country, in India as well as in the world. And job opportunities are continuing to grow. We are looking at new creation of lakhs of jobs in this sector in the coming years. There are the ESDM industry is cyclical, so it goes through peaks and valleys. But if you look at the overall trajectory over a decade or longer, there has been just nothing but continuous growth. So slowdowns are just a temporary effect, but over a period of time, it rewards really good engineers really well. So semiconductor and product manufacturing is also happens to be the top of the agenda for our government, as we are looking to bring in you know uh, the chip manufacturers and product manufacturers to the country. Government, state government as well as central governments are also rolling out some great incentives for entrepreneurship to create indigenous IPs as well as create the new products for the India markets. And there are also public private partnership models for skilling to ensure that the kids that are in high school or in the college, they get the right exposure early on from the industry to understand what's required to educate themselves in a relevant field, and then eventually land a successful first step in the industry. So there are technical skills as well as there are soft skills, and I cannot emphasize enough, but it really takes a team to build a chip or a system. So teamwork is a very important soft skill. Similarly, attention to detail. This is an expensive devices that you're making. Mistakes can cost severely to the production and revenues. So attention to detail, teamwork, right, integrity. Some of these are very important soft skills to have, and communication, written and verbal. The timing cannot be better. Currently, the winds are very favorable to us as a nation because of geopolitical situation that is taking place. India as a country, we also have a huge demographic advantage. We have significant percentage of our population is young, under the age of 35. Our academic infrastructure, we have about 2,500 plus institutes in the country that teach subjects that are related to the ESDM industry. And if you look at the world over, students that went through our educational system in India have been successful all over the world, right? So that proof is in the pudding that we have really good academic infrastructure. This infrastructure is also being upgraded, and industry is also stepping in. Government is also stepping in to ensure that we prepare the next generation of leaders in this industry. And if you look at also the diaspora, right? If you look at academics, if you look at industry, we have people of Indian origin at many places, and they are ready to contribute. They're very excited to contribute to nation's journey towards a success in the ESTM. And among everything, if we as a country have to emerge in the top economies, if we to ensure that we provide good employment to our youth, ESDM is a crucial catalyst. Governments have realized, they are investing into it. Industries have realized that we have to think ahead and bring awareness and support system for the faculty, institutions, and students. So industry is also stepping in a major way towards preparing a longer term, well skilled workforce for the ESDM industry. So the question gets asked, right? All of this is happening, but are we ready, right? And of course, Chandrayaan 3 is our latest success. But it's not just today. We have been successful for many decades. Even today, if you think about what is the biggest buzz happening in the electronics, and that's electric vehicle. right? And in year 2001, we had indigenously designed and manufactured electric vehicle that we were shipping not only to consumers in India, but exporting to 26 countries. So that's our track record as a country, as a talent, right? As entrepreneurs, what we can do, right? So it's really, will India succeed as a major player in the ESDM? The answer is with you, right? It's with the next generation of emerging youth, the, those among you who are in the schools, in the high school, those among you who are in undergraduate, graduate programs at the universities, right? Just don't look at the compensation or other aspects. Those are important aspects, but I think it's important for you to find what excites you, right? And what creates a passion in your heart. And if ESDM is a domain that you want to embark upon, right? uh, I think India would be lucky to have you, and I think you will find a great journey for your career and dreams ahead, locally as well as globally. So, with that, if I've created here more questions than answers, then let the journey of self-discovery begin. In today's world of Chat GPT and Google's and Bing's and so on, right? Uh, you inquire, you experiment, you create, and you lead, right? And we are here to support you. We have a website. We also have a LinkedIn webpage called Semiconductor Nation Campus Connect. If you follow us there, you'll find a lot of updates of what are the latest and greatest happening in terms of industry happenings as well as in terms of skilling and career related discussions. So with that, I would like to thank you for making your time today to join us, and hope you took away something useful out of your hour, and wish you a great success in whatever you choose to do ahead. All the very best. Thank you.
Thank you so much, Pradeep. That was a fantastic session. And trying to answer some of the questions on the chat box, but we do have one question from Subhranshu Adhikari. He was asking, when the round wafer is cut into square dice, there must be some wastage of the wafer at the corners. Are they rejected?
That is correct. The wastage is rejected.
We didn't have any more questions after that. So we really appreciate everyone's participation. Please do spread the word. We will be having this monthly, and we appreciate your time today, and we enjoy the rest of your Sunday. Pradeep, thank you so much for the fantastic presentation. The slides will be available archived on the IESA Online YouTube channel. Please share that link with others who might be interested in careers in semiconductors and electronics.
Thank you, sir. Thank you, everyone. Good night.